So let me start by summarizing the main ideas from last time. So the main idea was that we have, for a vector space, we have these spanning sets. So what's a spanning set? If you have a vector space, you pick a set of finite number. Well, pick a set of number, pick a number of vectors So let's say you have these. Because I just picked n vectors. And if I make all linear combinations of these vectors, all possible linear combinations, that would be span of W. And if this is equal to, if this span is the total space, V, from which I picked these vectors, then this set sort of is all I need to construct the whole vector space. I take this set, I take these vectors and make linear combinations, and I get the whole vector space back. So that would be then a spanning set for V. And we saw, so an example in geometric space would be that if I'm in 2D, then I can have these ij unit vectors. These unit vectors I and j, and I can construct any vector in 2 dimension by a linear combination of ij, because any vector in 2D can be written like this. So all linear combinations of I and j give me back the whole 2-dimensional plane. And if I have a third dimension, I can include another vector k, then this set ij and k is one spanning set. Because in 3D, all vectors can be written as linear combinations of ij and k. So in 2D, this is one spanning set, and in 3D, this is a spanning set. But if I come back to 2D, I can include this vector, some arbitrary vector in this 2-dimensional plane, and this set I, j, and b is also a spanning set, because if I make linear combinations of these 3 vectors, they also form the full, they also give me back the full vector space. But we know that this is like more than what we need. We saw last time as well with many examples that in a spanning set, you may get rid of some vectors and still be able to generate the whole vector space. So like in this set, I can get rid of V, and I know that ij, which are left back, still span. Or I can get rid of j, and iv still span the whole space for me. Any 2 vectors in a plane, if I make linear combinations, I'll get all the other vectors back. So this idea that some of the vectors, so what can happen that in your set W, some vectors may be a linear combination of others from the set. Some vectors in W may be a linear combination of others from the same set W. So then you don't need those because everything you were writing as linear combination of these vectors from V1, V2 to Vn can be written if you delete these vectors which are already linear combinations of others. So this idea that some of them may not be independent vectors, may be just constructed out of the other parts, other vectors in your set, this is captured in the concept of linear independence. So you sort of want minimum number. You want to retain minimum numbers of vectors from the set which you absolutely need, which cannot be written in terms of the other vectors from the same set, from the same spanning set. So a set of vectors is linearly independent if none of them can be written as a linear combination of others. And this happens if and only if you have this condition satisfied, that if you make a linear combination of the vectors in your spanning set or of any set, it doesn't have to be spanning, any set, this concept is defining linear independence for any set of vectors. If I make a linear combination, this has, if this has only solution, that all of these Ci's, you have to put them equal to 0. And on the other hand, if a non-trivial solution exists, if this is satisfied, let's call it equation 1. If 1 is satisfied for at least one Ci not equal to 0, then they are linearly dependent. And at least one of them can be written as a linear combination of the others. Of the others. Now the idea is, so using these concepts, the main idea for today would be the following. That I define a basis. So what's a basis? You have a spanning set, or maybe let's write it like this. A set of vectors forms a basis for a vector space if and only if they are, first of all, they have to be linearly independent. And secondly, it spans the vector space. So in a sense, it's a spanning set. You can use it to construct all the vectors in your vector space, but you cannot get rid of any one of them in favor of the rest of them because they are all linearly independent. None of them can be written in terms of the others. So it's kind of a minimal set. But it's a one, you can have many bases. We will see how many bases you can have in a vector space. So any one particular set which has these properties, you pick a number of vectors from your vector space and they satisfy these two properties that they are linearly independent and span V, you have got a basis. So for example, if I pick in R3 these vectors, clearly these are linearly independent because if I make a linear combination and put it equal to 0, this implies, because the C on this on the left hand side, I get this. So this means this linear combination can be zero vector only if all these constants are 0. So remember, we have this geometric interpretation of these column vectors. If you have one on the top, you can think of it as the representing the coordinate of the x-axis. This vector, the I vector, and this guy is the j vector, and this guy is the k vector, and so on. If you have R4, you can imagine that there is a third axis, which you cannot imagine, but there will be a unit vector, a vector related to that, which will be written like this. So this set, which you can also call the set ijk, is linearly independent, and clearly we can write, if I made this linear combination, A, B, and C you can choose arbitrarily. You are spanning through this set. The span is all possible vectors in R3, since A, B, and C are arbitrary. So this set is a basis. This is a basis. So you're familiar, I, J, K unit vectors form a basis. But that's not the only basis. I can quickly give you another example. Another basis. For R3, and I'm picking this set. I throw in this vector, and this vector. So these are three vectors picked up from R3, and we saw last time that if you have same number of vectors as the dimension of as the number of components you have in the column vectors, then you can easily check if they are linearly independent or not by computing the determinant of this matrix. Put these vectors inside a matrix, construct this matrix, and check its determinant. So determinant of this guy is 1 into 1 minus 0. I get a 0 from here, don't need it. Then I have a 2 into 1 minus 1. So determinant is 1, which is not 0. That would mean that these are linearly independent. They will be linearly dependent only if this determinant is equal to 0. Also, I can write, I have to now check if they span the space. I have checked the first condition that they are linearly independent. Now I have to check if they span the whole space or not. So I make a linear combination. And this should give me any arbitrary vector from R3. So I should be able to make any real numbers alpha, beta, gamma on the right hand side. But this same equation, we are now quite familiar. I can write it as a matrix equation. This is how the multiplication, one rule of multiplication of matrices with vectors was this, that you take this coefficient and make the linear combinations of the column vectors. So it is this equation. A times this vector, this is x, is equal to B vector, this is B. For given B, I have to look for X. I have to look for A, B, C. If I can find some A, B, C so that I construct the given B. But since A's determinant is not 0, since A is non-singular, so I can multiply both sides by A inverse. This means X exists, you have a unique solution. So you can find A, B, and C for any alpha, beta, gamma. So that just shows that this set spans the whole R3, so it's a basis. So the given set was a basis. Now, what we saw was like in this 3D, I had this I, J, K as a basis, but then I found some other vectors which were also linearly independent and spanning. And they also formed a basis, and they also were 3. So I want to have an idea that in a basis, how many vectors are there? What can I say about how many vectors are needed in a basis? So to that end, I have first this very useful theorem. This will be very useful in other contexts as well. So if you are given any spanning set with n vectors, it's not necessarily a basis. All you want then is a spanning set. If they were happen to be linearly independent, then it would also be a basis. But for any spanning set, if you are given a spanning set which has n vectors, then any other collection of m vectors, another set, you pick another set with m vectors with m bigger than n. So you are given one set which you know is a spanning set. Its linear combination can create all vectors and it has n elements. Now you pick any other vectors from the vector space which are m in number and m is bigger than n. Then you know, this theorem tells you, then this collection of m vectors is linearly dependent. They just cannot be linearly independent. So what's the proof? So suppose you are given this collection U1, U2, Um with m bigger than n, then you can write, since V1, since these guys span the space, that means each of these U's can be written as a linear combination of V's. That's the very meaning of this spanning. So you have A1, 1, V1, the first one can be written like this. And so on. So a typical UI, it will have, it will be some linear combination of these. So I am writing it like this. Now to check if these are linearly independent or not, we have to check this equation, make a linear combination of these guys, use there are m of them, and put it equal to the zero vector. And now we have to see if we can find a non-trivial solution. A solution where not all C's are zero, and if we can still make a zero vector on the right hand side. So this linear combination, I can replace the U's inside over here. So this guy is equal to 1 to m Ci Ui, but Ui themselves are linear combinations of Vi. So like this. Now it's just a double sum, so I can interchange the order of summation. I can first sum over the j's. So I have this equal to this, and this has to be equal to, could equal to the zero vector. Now if I consider, I'm looking for these constants over here. So let's consider this equation. Where j are from 1 to n. Now I'm looking for these constants, Ci. Remember, this is the equation which you are trying to solve. You're looking for Ci so that this becomes 0. And I'm looking for non-trivial solution where these Ci's are not 0. But over here, if you see, you have I goes from 1 to m, and you have, so number of C's which you are looking for is m. But how many equations you have? For each j, you have one equation. So your number of equations is n, and m is bigger than n. So that means you have more unknowns than the constants, more unknowns than the equations. So you're trying to solve this kind of equation. You have more columns here and less rows here. And on this side, you have all zeros. So if you recall, if you on the right hand side you have all zeros, then your equations can never be inconsistent, because for inconsistency on over here you must have a row in the row echelon form. In the reduced row echelon form, you must have a row of zeros in the original matrix, and on the right hand side you have a 1. But since the right hand side is all zeros, is never going to change, so this is always going to be consistent. Also, because you have more columns, so you have more unknowns, then you can have the lead variables, less rows. So some of the unknowns will be free variables. So you do not have a completely trivial solution. You always have, when you have more equations, less equations than the unknowns in a homogeneous system, then you have a non-trivial solution. We had discussed it many times. So this means a non-trivial solution exists with not all Ci's equal to 0. So that means UIs are linearly dependent. So our set, any set, if I have one spanning set in my space which has n vectors, find any spanning set and I count its number of vectors, then I pick another set with more than those vectors, I'm guaranteed that this new set is going to be linearly dependent. So this has a very striking consequence. And the consequence is the following. Consequences in maths you usually write with this fancy word corollary. So the consequence is that if you pick two bases, any two bases, so this is a basis, and you have another basis. In the first basis, so you have n vectors. In the second basis, you have m vectors. Then actually they must have same number of vectors. So all bases in a vector space have to have same number of vectors. We saw some examples. The examples we were considering, in those they happen to be same, but now we have a proof. So how do I prove it? This proof is just using the previous result. So since this set is a basis, so it spans. It spans V. These are the two properties of a basis. It can span the whole vector space, and these vectors are linearly independent. So this spans, but this set is also a basis. So it is linearly independent. In the first one, I'm using the first property. For the second set, I'm using the second property. But from the previous result, previous theorem, this means that this M, since they are linearly independent, M cannot be bigger than N. M has to be smaller than N. But now I can reverse the role and say since W1 span the vector space, and these guys are linearly independent because they are bases. This is only possible if N is less than M. So these two conditions, A and B, can be satisfied only if N is equal to M. So you have found a kind of a very superb result that all bases in a vector space have same number of vectors. So this, because this is a fixed number, this is a very important property of a given vector space. So you call it the dimension of V is equal to number of vectors in any of its spaces. Because all of them have same number of vectors. Now, for example, since I know that all subspaces are vector spaces, so they will have a basis. Actually, I haven't really proved it. We will see it along the way. But if they have a basis, then their dimension would be fixed. They will have a basis, and the number vector in that will be the dimension of the subspace. And the dimension can vary for the subspaces from 0, 1, 2, up to n, which is the dimension of your original vector space. When the subspace has dimension n, So I'm saying W is a subspace of V. When the W has subspace has dimension n, it's actually the original space. So it's kind of improper subset of V. And what is this dimension 0? Well, if you just pick the 0 vector from your original space, it's just one vector. It's also a subspace because it fulfills all the properties of a vector space. You can make any number of linear combinations, you still get back 0. So it's a vector space. And so this is given the dimension 0. If you pick any let's say, non-zero vector and start making its linear combinations, this space will have dimension 1. So if, like in some examples, we have seen that we have more than one basis. So far, we have found out that all of these bases are going to have same number of vectors. But let's think about how to pick a basis, how to find some vectors which will do the job of being a basis. That means spanning the space for me while being linearly independent. So how to pick a basis? Well, there are an infinite number of ways, actually. So there are infinite number of bases. But how to pick some of them, how to pick any one of them? Well, the first thing is, if you know that your vector space has dimension n, you're given this, then pick any n linearly independent vectors and you don't even have to worry about if they span or not. They will. You are guaranteed that they will span the vector space. Pick any n linearly independent vectors and they will form a basis. How do we see it? So to show we have already picked them to be linearly independent, n of them. All we have to do is we need to show that they span V. So suppose you have picked these guys, V1, V2, Vn. This set is linearly independent. Then you pick any other vector from your vector space. Now, since I know that the dimension of my vector space is n, so there exist n vectors that span V. Because that's the definition of the basis of the dimension, that number of vectors in one of your bases. Since its dimension is n, so there will be some basis which will have n vectors. So those n vectors will be spanning this space. But we did that theorem above that if you have a spanning set with n vectors, then any collection of vectors which are more than n is going to be linearly dependent. So I take my chosen n linearly independent vectors and add to them this n plus first vector v, one more vector v. So now I know that they are going to be linearly dependent. This set must be linearly dependent. That means that there will be a linear combination of these vectors equal to 0 with not all Ci's equal to 0. So at least one of them have to be non-zero. Now, C cannot be 0 because if C is 0, then this equation is saying that if C is 0, that would mean putting C back 0 back in equation in above equation, you will have is equal to 0 with at least one Ci not equal to 0. But that would mean that this set, your original set, is linearly dependent. That these vectors among themselves are linearly dependent. But that's a contradiction. We assume that they are not linearly dependent. Therefore, C is not equal to 0. If C is not equal to 0, then this equation, let's call it 3. Then from 3, I can take them to the other side and divide by C because C is not 0. Now, V was arbitrary element of the vector space other than these n vectors. And I have written it as a linear combination of these n vectors. So this just means any vector can be written as a linear combination of these n vectors. That means these vectors span V. So only if you do only half the job, pick n vectors which are linearly independent, you are guaranteed that they will form a basis. It works the other way as well. If you have n vectors in and you know that you are in a vector space whose dimension is n, you pick n vectors that span V, then you already know that they will be linearly independent. Then they will be linearly independent, or they will form a basis. How do you see this? You have to show that they are linearly independent. So these two, I'm going to prove it, but these two statements tell you that you have to do only half the job. You know that the dimension is n, so any basis is going to have only n elements, exactly n elements. And if you pick n linearly independent vectors, you are guaranteed that they will span, and so they will be a basis. While if you pick n vectors which span the vector space, you are guaranteed that they will be linearly independent. So they will form a basis. So suppose we have to show that they are linearly independent. Now suppose that they are linearly, let me write it this way, linearly dependent. What would that mean? That would mean that at least one of them can be written as a linear combination of others. As linear combination of others. And that means if I remove that, the remaining n minus 1 vectors still span the space. Now these remaining n minus 1 could be now linearly independent or linearly dependent. If they are linearly dependent, what would happen then? Then again, there will be one vector among them, among these n minus 1 vectors, which will be a linear combination of the others. So I can remove that 2 and work with n minus 2 vectors. Those n minus 2 will still span if these n minus 1 are linearly dependent, then one of them can be removed so that the remaining n minus 2 still span. If these were linearly independent, what would happen then? That would mean that I have n minus 1 vectors which span the space, n minus 1 linearly independent vectors which span the space. But that would mean that I have a basis with n minus 1 vectors, which is not possible. On the other hand, if they are linearly dependent, then I can take out one more so that I have n minus 2, and I keep doing it unless I'm left with some k vectors less than n which are linearly independent. By reducing it, finally I'll have k vectors. I will have k vectors that still span and are linearly independent. So I will have a basis with n vectors, with k vectors less than dimension of V, which is not possible. All bases have to have same dimensions. Well, you may suspect maybe I'll never get a linearly independent set. You will, because k can be 1. If you have only one vector, that is always linearly independent. Because if you keep reducing, you either hit k vectors which are linearly independent or come down to one vector. But one vector alone is linearly independent. It's not depending on anything else. So you will have then dimension of V equal to 1, but we assume that dimension is n. So this is not possible. It's a contradiction. That means our starting point that they are not linearly independent, that they are linearly dependent is wrong. So pick any n vectors which span, they will automatically be linearly independent. So the converse of this picking of vectors, kind of converse, is also true. So for example, you can prove this sort of many results for a vector space of dimension V of dimension n. No set of vectors no set of fewer than n vectors can span V. We know that we will not find a set of a set of let's say k vectors which is less than n, which is linearly independent and spans, because we saw that the basis is fixed. But actually you will not be able to find any set which is doing this job. Because if you have again using the previous logic, m vectors which span and m is less than n space, let me write it clearly, then they will either be linearly independent, they are either linearly independent, but this leads to, if this condition is true, this is a contradiction, because then you have a basis they span and they are linearly independent, so they are a basis with m less than n, which is not possible. We proved it. Or they are linearly dependent. But if they are linearly dependent, again, I can start deleting vectors while still spanning my space. So I will hit a set with k vectors less than m, less than n, that still span. And finally, they are linearly independent. So I'll have a basis with k vectors less than n. Contradiction. So not possible. So no set of fewer than n vectors. You are given a basis, you have to have at least that many to span the space. So basis is very, very fundamental. is the minimal set which spans the vector space. And you are guaranteed that this minimal set has same number of vectors. You can choose different vectors to throw in this generating set, but every time for a given vector space, you have to pick same number of vectors. And then you can also show that any linearly independent vectors where k is less than n, so you have got k linearly independent vectors, can be extended to a basis. So in a basis, you have to have, if you pick any n, I know that if I pick any n linearly independent vectors, it will be a basis. So I'm already given k of them. This result says you are guaranteed that you will be able to find the rest of, to include in this basis, keep these k, and you will be able to find the rest of the vectors which are linearly independent with them to complete your basis. How can you show it? Well, if I consider this vector, which is in the span which is not in the span of this. So the span of these vectors will be a subspace. We saw this result that the span of any set is a subspace. Span is a subspace of V, but this is not equal to V, because if the span is equal to V, that would mean that this is a basis. We just proved above that less than n vectors cannot span. So it will not be in the span. If it's not in the span, that means Vk plus 1 cannot be written as a linear combination of these guys. But we learned that this is just a condition, another way of saying that this is linearly independent with these. So these vectors, they become linearly independent. So I've extended my set with one more vector, so that the extended set is still linearly independent. Now again, I span, I'll again find that there are still some vectors which are not in this span. So I pick any vector from that complement which is not in this span, that will be linearly independent with these. So I keep finding until I complete my basis of n vectors. Similarly, you can lastly do this, that you pick any spanning set, you can delete vectors to get a basis. You don't have to discard the whole set. You have a spanning set and it turns out that it's not linearly independent, so it's not a basis. It has more vectors than you need. It's not that you have to pick a new one. You will be able to find a complete basis from within this set. You can delete the extras and some of them will still form the basis. So I'll leave this as an exercise to prove it. Instead, let me come to some examples. Well, before examples, this is just a definition, standard basis. So we have seen we can pick many, many bases. In fact, infinite number of bases. But in Rn, you have the standard basis. You call them EIs, and in the EI, you have a 1 at the ith location, and all the rest are 0. So for example, if I'm considering R4, if I pick these guys, this is a basis. They are all linearly independent and they can generate the whole space. This very simple looking basis, this is called, because this is so simple and so obvious, it's kind of natural. Although not advantageous over the others in all situations, but it's very simple and natural. This is just called the standard basis. Similarly, for example, if I consider this space, 2 by 2 matrices, over there you can give a standard basis. The other bases are not any less than these. It's just one choice, which is like easy to pick. Over here, I can again pick a very easy basis. You can show that this is a basis, and this I will call just the standard. We saw that the polynomials of degree n, they form a vector space, and you can show that these vectors form a basis. Clearly, well, let's think about it. This is very easy, that they span. This guy, they span all polynomials. Because polynomials, by definition, of n degree are of this form. Now, these are just linear combinations of this set. Of set, let's call it W. Well, let's call it B for basis. So they do span, and I cannot make, if I put this equal to the 0 vector, which is just the 0 number, how will I get it? I have to put a not equal to 0, a1 equal to 0. If any one of them is not 0, I don't have the 0 on the right hand side, because I only add the equal powers of the variable. So they are linearly independent. So they are a basis. And this basis is called, for polynomials, the standard basis. So now let's take an example. So I consider a subspace of polynomials of degree, let's say, I can even take n, is subspace of polynomials of form, this form, where a, b are any arbitrary numbers. The question is, what is the dimension of this subspace? Well, I can write these as this. X plus 3. So this is showing me that if I pick this polynomial, call it one polynomial, this is, let's call it P1, let's call it P2, and this polynomial, all the polynomials are linear combinations in the subspace of these two. So x squared plus 2 and x plus 3 span this subspace. Also, these guys, I have to check if they are linearly independent or not. If I put this equal to 0, I have a x square over here. This cannot be cancelled with any x. So coefficient of x square has to be 0. So that means C1 is 0. Similarly, I have a single x on in the second term, and coefficient of this has to be 0 to get the 0 on the other side. So this can be 0 only if this is true. So that means P1 and P2 are linearly independent. But that means I have found a basis. I found a basis for the subspace, and it had two elements. So it means, and the basis was just this. Dimension of this subspace is 2. Let's consider this example. You are in R4 and you consider a subspace S of all these vectors of this form. A, B, C are arbitrary. So I can write these elements, the vectors in the subspace, as So all the vectors in this subspace are linear combinations of these three guys. So I have a spanning set. I found a spanning set. Now I have to check if they are linearly independent or not. For that, I again make a linear combination and put it equal to 0 vector. So that means this is a linear combination. Let me make a new one. And put it equal to 0 vector. So this means C1 plus C2, C1 minus C2 plus 2C3, C3, sorry, C2 and C3 is equal to 0. But this means that C3 has to be 0 and C2 has to be 0. And if I put it back over here, this also means C1 has to be 0. So I can only make a 0 vector if all the coefficients are 0. That means they are linearly independent. And this is a basis. Basis has 3 elements. That means dimension of this subspace is 3. So I'll stop here.